All right, so Unit 8 review. So this one is on statistics. Okay, number 1. In watching auditions for lead singer in a band, Liam became curious as to whether there is an association between how animated the lead singer is and the amount of applause from the audience. He decided to watch each singer and rate the singer on a scale of 1 to 5, where 1 is the least animated and 5 is the most animated. He did this for all 5 nights of auditions and found that the more animated singers did receive louder applause. The study Liam conducted would be best described as, okay, I think the key word here, I'm going to underline it, is watch. All he did was watch what went on, so that is called an observational study. In an experiment, right, the person conducting the study intentionally intervenes. He randomly creates 2 groups and keeps all the variables the same other than the one aspect of what they're testing for. So this is definitely not an experiment. A survey is usually just, some sort of questionnaire that's given out. And random assignment, that's actually what's done when you do an experiment, right? You want to randomly assign the participants to certain groups. So in this case, he's just simply watching, he's observing what the outcome is. Okay, number 2. Cheap and Fast Gas Station is conducting a consumer satisfaction survey. Which method of collecting data would most likely lead to a biased sample? Okay, so a biased sample is caused because the study was not conducted properly, so it may lead to inaccurate results. Okay, so let's see. Choice 1. Interviewing every 5th customer to come into the station. Well, that's actually a good way to do it because that's very random. So I'm going to say that's not our answer. Okay, choice 2. Interviewing customers chosen at random by a computer at the checkout. Well, that's a good way to do it too because they're randomly choosing their participants. Okay, interviewing customers who call an 800 number posted on the customer's receipts. Okay, this right here, this is going to lead to a bias sample. Whenever you ask people to call in or self-report, a lot of times that leads to biased results. So this right here is going to be our answer. The reason why number 4 isn't is, let's say, interviewing every customer who comes into the station on a day of the week chosen at random out of a hat. Again, this is randomly chosen, so that could produce, good results. All right, next one. So number 3. There are 440 students at Thomas Paine High School enrolled in U.S. history. On the April report card, the students' grades are approximately normally distributed with a mean of 79, I'm going to just underline that, and a standard deviation of 7. Students who earn a grade less than or equal to 64.9 must attend summer school. Okay, so if they earn a grade less than or equal to 64.9, right, they must attend summer school. The number of students who must attend summer school for the U.S. history is closest to. All right, so now here, because we're looking at a normal distribution, I don't know if you guys remember, but we can use normal CDF. And when you do this, let me just write this out. There's 4 numbers that are important. We need to create a lower bound and an upper bound first. So because it's less than or equal to 64.9, this 64.9 is going to be our upper bound because we're looking for everything lower than it. So for your lower bound, you could either use 0, or I like to just use a negative with a whole bunch of 9s, although technically you can't get a negative score. So even if you put 0 there, that's perfect. All right, and then my upper bound is 64.9. And then after the next comma, we put the mean, which we saw was 79. And then our final number is going to be our standard deviation, which we see as 7. Okay, so what we want to do is we want to type this in the calculator. Okay, so in the calculator, see right here where it says distribution, we're going to hit second and then distribution. It's actually second bars. And number 2, you're going to scroll down to that. I just hit the number 2. Says normal CDF. Here, I'll show I'm scrolling down just so you see it. We're going to hit that one. And then it gives us our lower, upper, mean, and standard deviation. So for lower, I'm just plugging in negative 99999. And if you plug in 0, that's fine. For the upper, we said that was 64.9. For the mean, that's going to be 79. And then for the standard deviation, we're going to replace that with 7. Okay, and then we just go down to paste and hit enter. When you hit enter again, this gives you the percentage of students who must attend summer school. Okay, so let me just put that on the paper. It's about, let me do this. I'm gonna say it's approximately 0.02199. Now that's the percentage. We wanna know how many. They want us to find the number of students. All right, so we're gonna need to multiply that percentage by the 440 students that are in the school. So we're gonna multiply this by 440. All right, so let's do that in the calculator. Let me hit times 440, and let's see what we get. Okay, so that rounds up to about 10 students. So it's approximately 10. So choice 3. Okay, number 4. A study was conducted in 2004 in New York City and found that 212 out of 1,334 participants had hypertension. Kim ran a simulation of 100 studies based on these data. The output of the simulation is shown right here in this diagram below. Okay, at a 95% confidence level, the proportion of New York City residents with hypertension and the margin of error are closest to what? Okay, so the first thing they want us to find is the proportion of New York City residents with hypertension. Well, look at this. They told us this right here. 212 out of 1,334 had hypertension. Okay, so if you plug that in your calculator, you see that's equal to about 16%. Okay, so far it has to be either choice 1 or choice 2. So I'm going to cross off these two, choice 3 and 4. Okay, now they also want us to find the margin of error. Okay, so if we use our margin of error formula, right, we know the margin of error. Well, we have two formulas. Margin of error is either equal to 2 standard deviations, which they don't give us. So the other formula we can use is 2 times the square root of P times Q over N. Okay, so this is going to be equal to 2 times the square root. Now the P is the expected outcome, right? The proportion that we expect to occur, which we just found right here, is 0.16. So I'm going to replace that P with a 0.16. Now Q is just equal to 1 minus P. So 1 minus 0.16. So 1 minus 0.16 is 0.84. Okay, and the N is the sample size. So let's see. Here we go. 1,334 participants. So that would be our sample size. So all you're going to do is just plug this entire thing right here in the calculator and see what you get. All right, so when I do, let's see, I get approximately 2%. Okay, so we could see that choice 2 is our answer. All right, number 5, the results of simulating tossing a coin 10 times, recording the number of heads, and repeating this 50 times are shown in the graph below. Okay, so here we have it. So we want to know, based on the results of the simulation, which statement is false. Okay, so we're looking for which is not true. All right, so number 1 says 5 heads occurred most often. So here's 5 heads. That definitely did occur most often, which is consistent with the theoretical probability of obtaining heads. Yeah, that's the theoretical probability. Half of the time you get heads, so 5 out of 10. So this is a true statement, so that is not our answer. Okay, I'm going to actually come over here to choice 3 next. Obtaining 3 heads or fewer occurred 28% of the time. Okay, so here's 3 heads or fewer. So let's see, if we look at 3 or fewer, so let's just add these up real quick. Just counting up the number of dots, and I got 14. So let's see, there's 14 of these out of, now we said over here that there were 50 dots altogether, so 14 out of 50 is equal to 0.28, which is 28%. And that's what this says, so that's a true statement, so we're going to ignore that one as well. Or not ignore it, but cross it off. All right, let me just get this stuff out of here. All right, so then I'm going to actually take a look at these two together because they both talk about the middle 95%. So the middle 95% is like which dots would make up which dots in the middle would make up 95% of this data? Well, let's see. If there's 50 dots altogether, Okay, well, 95% of 50, we'll just multiply that by 0.95, is 47.5. Okay, I'm just going to round that to 48, right? So let's say the middle 48 dots make up the middle 95% of the data. So if there's 50 dots altogether, we want to look at the 48 in the middle. Well, this one, that means there's going to be one left on the outside of each side of the 95% confidence interval. So this dot right here is outside the 95% confidence interval. Then I'm going to work my way this way. I'm actually going to stop here. Even though there's 2 dots out here, right? Even if I wanted to throw one of these in here. Anything in between 2 and 8 heads is in the 95% confidence interval. Okay, that makes up the middle 95% of our data. All right, so let's see. 8 heads is unusual. Well, if 8 heads is in the 95% confidence interval, it is not unusual. So it says as it falls outside the middle 95%. That is not true. That lies within the middle 95%. So this is our false statement. And then if we just look at choice 4 says 7 heads is not unusual. Okay, that's true. As it falls within the middle 95%. So that's true. All right, so choice 2 is our answer. All right, number 6. In a random sample of 250 men in the United States, age 21 or older, 139 are married. The graph below simulated samples of 250 men 200 times, assuming that 139 of the men are married. All right, so this is what we have right here. Now, if you notice, they show us the mean and they show us the standard deviation. So whenever you see this, a lot of times we want to find the 95% confidence interval. And when you read letter A, look, it says it right here. Based on the simulation, create an interval in which the middle 95% of the number of married men may fall. Round your answer to the nearest integer. Okay, so what they're looking for us to do is they're looking for us to take the mean and subtract off as well as add on 2 standard deviations. That's called our 95% confidence interval. Okay, so I took the mean and I'm going to subtract off as well as add on 2 standard deviations. Okay, so when I do that, let's see. They want us to round to the nearest integer. So when I subtract off 2 of these, I wind up getting 123. Okay, I'm rounding that to the nearest whole number, nearest integer, which makes sense because we're talking about the number of men, so you would have a whole number, right? And then when I add on 2 standard deviations, that rounds to 155, right? So this is my 95% confidence interval. Okay, so I just wanted to show the calculator work right here, and that's where I got these numbers from. Okay, so part B says, a study claims 50% of men 21 and older in the United States are married. Do your results from part A contradict this claim? Okay, so first of all, we were looking at 250 men, right? So when it says 50% of men 21 and older, we want to figure out what's 50% of 250. So basically just half of 250, right? So that would be 125 men. Okay, so do your results from part A contradict this claim? Well, no, they don't contradict the claim. It actually supports the claim, right? Because 125 is within the 95% confidence interval. Okay, so you're just going to write that out and make sure you say, make sure you use the wording, the 95% confidence interval. Okay, and finally the last one. To determine if the type of music played while taking a quiz has a relationship to results, 16 students were randomly assigned to either a room softly playing classical music or a room softly playing rap music. The results on the quiz were as followed. Okay, so we could see these were the scores from the classical room, and these were the scores from the rap room. John correctly rounded the difference of the means of his experimental groups as 7. How did John obtain this value, and what does it represent in a given context? Okay, so let's first talk about how did John obtain this value? Well, let's think about it. Isn't mean another word for average? So John averaged together the scores of the classical group, right? He added them up and divided by, I guess there's 8 of them here. And then he found the average of the students in the rap group. So he added these up and divided by 8. And then he found their difference. And when he did, this answer rounded to 7. Now, you could either show the work for this. When they said, how did John obtain this value? You could show the work. You can find the average for this, find the average for this, and then subtract them. I actually wrote it out in words, so I'm going to show you what I wrote. Okay, so I said that John took the sum of the classical scores and divided, here, this is supposed to be 8. It's hard to see, and divided by 8 to get an average of 82. I mean, you could show that. You could show that you're adding these up and dividing by 8 to get 82. He also took the sum of the rap scores and divided by 8 to get an average of 74.625. Okay, he then subtracted these values to obtain a mean difference of 7.375, which rounds to 7. So I put this in words. If you want to show work instead, you can do that. Okay, now it wants to know, and what does it represent in the given context? All right, so the mean difference is positive 7. So what that means is that on average, the students that were assigned to the classical group scored 7 points higher, right? Remember, we said on average, than the students who were assigned to the rap group. Okay, so I'm going to write that out in words. I'm going to take a picture of my work, though. Okay, so the students that were assigned to the room playing classical music scored 7 points higher. I'm going to actually underline this on average because a lot of people forget that. Right? It's not in total, it's on average. Than the students assigned to the room playing rap music. All right, so now let's take a look at what we have on the bottom. Okay, so to determine if there is any significance in this value, John re-randomized the 16 scores into 2 groups of 8, calculated the difference of the means, and simulated this process 250 times as shown below. So that means there's 250 dots right here. Does the simulation support the theory that there may be a significant difference in quiz scores? Explain. Okay, so what we want to do is if we want to see if there's a significant difference, we want to locate where the difference of 7 is, right? Because that was our difference. So 7, well, if this is 5, this would be 6. 7 is right here. And we want to look at not only that difference, but anything even more extreme, like anything that has an even bigger difference, more than 7. So, I mean, the only one that has a bigger difference than 7 is this one right here, which is 8. So we're going to take a look at these right here. So altogether, if you count up the dots, we have 1, 2, 3, 4. So there's 4 dots. Now that's 4 out of this 250. Okay, so 4 divided by 250 is what, 0.016? So if we move that over twice, that occurs approximately, or actually exactly, I should say, 1.6% of the time. Now, if something is a significant difference, it means that it's such a big difference that it's rare to occur, right? It only occurs, it's not, that difference doesn't occur due to randomization of who was placed in what group. The difference is so big that it occurs because of, in this case, the 2 different music styles that were given to the students. So we could say that yes, there is a significant difference because a difference of 7 or more occurred less than 5% of the time. So here we go. Right here, the simulation supports the theory that there may be a significant difference in quiz scores because a difference of not just 7, right? 7 or more, that's why I underline that, occurs less than 5% of the time.